all set? How's everyone doing? Good? Awesome. All right, let's get started. A bunch of logistics to cover first. So first, office hours for me are going to be on Thursdays, so in the afternoon, 2:30 to 4. And for now, I'm planning to host them in my office, so Morgridge 5514. If you guys come and we don't have space, we'll figure out a new room, but that's the plan for now. If there are folks for who that doesn't work at all, just shoot me an email. We can either find a different time or we can potentially switch the whole thing. I'm going to start posting a bunch of resources. This is the first one. So this is a pretty interesting overview of ML. This is written by Moritz Hart and Ben Recht. And the book should be available online if you go to that website. I quite like it. It's not meant to be like a comprehensive intro to AI and ML. It's something much shorter, which gives you a bunch of intuition and tries to explain where a lot of things came from. So it's quite good. Ben was actually a professor here in the CS department about 10 years ago. He's at Berkeley now. Let's also briefly talk about where the class is going. So today is just going to be this mini review. We'll talk in a second about what we'll cover. There shouldn't be too much new for today, but you'll at least get a sense of where are we going and why do we need all the new stuff that we need for foundation models. Then afterwards, we're going to jump in. So on Thursday, we'll jump into transformers. We'll try to go very much bottom up. So we'll try to build every operation kind of from the lowest level and gradually understand what each of the blocks are doing. And then eventually we'll use them to build up models. We'll be mostly focused on an operation that's called attention. We'll start talking about what that is today. And then on Tuesday, we'll talk some more about other architectures. My guess is that we're not going to finish Thursday in time, so we'll kind of move into Tuesday. We'll also start talking about these alternatives to transformers. One thing that we'll learn is that transformers are computationally expensive. They are sequence-to-sequence models. Whenever we talk about sequences, what we care about is their length. And if we want to plug a whole textbook, for example, into a model, the number of words or tokens that textbook is going to be hundreds of thousands. So one thing that we'll see is that kind of the vanilla transformer has an operation that scales with the square of the sequence length. And that means if you want to plug in a textbook, you're going to have to deal with the square of the length of the textbook. That's going to get very long. So for that reason, a lot of what's being proposed now are things that get rid of this quadratic issue. And these are going to be all called subquadratic models. So we'll talk about those next week. Then afterwards, we'll jump into how do we build language models with these things. So now that we've developed some new deep learning architectures, how do we actually go ahead, build up our language models, see what they look like, how they work, what they do? Any questions so far on kind of where we're going? Any questions on logistics more broadly? Nope. Awesome. Okay, so let's talk about what we'll talk about today. So 3 areas that, again, hopefully everyone's already pretty comfortable with. This is just going to be stuff that we basically need so we're all on the same page for the rest of the class. The first one is just general supervised learning. So this is going to be the stuff that basically we can no longer do that's going to motivate us to care about foundation models in the first place. So what kind of features do we have access to? What are we predicting? What are labels? What kind of model classes do we care about? What kind of training procedures are we going to use, et cetera? So that'll be a very brief kind of overview of what we guys have already learned for supervised learning. Now, all of these things apply to lots of different kinds of models, but in this class, we'll be almost entirely concerned with neural networks. So we'll occasionally talk about other things, but virtually everything will be a neural network, so we'll try to specialize that discussion to neural networks. Okay, so what kind of neural networks will we very briefly talk about? We'll start with perceptrons because they're the simplest. We'll talk about multi-layer perceptrons, about the way you do training, about convolutional neural networks. Very briefly, we'll cover kind of what came before transformers, which are recurrent neural networks and LSTMs. And then finally, stuff that you need to know about data augmentation, since we'll do. Then finally, we'll get to the piece that's really getting very close to motivating transformers and motivating foundation models as a whole, and that'll be self-supervised learning. We started talking about this last week at the end. We said the big kind of thing that we can't do anymore is create very large labeled data sets. We need to find some other signal for supervision. We need to find some other information that we can use to train models. And this is going to be all about that. How do we get good representations when we don't have access to a lot of labeled data? We'll be repeatedly doing this when we go train our language models, and more broadly, all of our foundation models. Anybody have questions about what we will talk about today? Great. All right, let's jump in. So this is going to be completely boring, but hopefully at least it will put us on the same page. Let's try to formalize the supervised learning setup. And supervised learning just means I have some information, I have some inputs, I have some outputs, and I want to design a model that's good at predicting the outputs from the inputs. So here's our problem setting. And the most annoying part about all of this is there's going to be lots of different terminology. We're going to use lots of different terms that are all equivalent, but they all came from different fields. Statisticians have one language for this stuff, machine learning people have one language, mathematicians a different one, and so forth. Okay, so the first thing we're going to do is get a set or a space of potential inputs or data points or instances. All of those for us mean the same thing. These are the things that we're going to have to plug into our models, and the space of those possible things, we're going to call it this cursive X. Okay, so this could be anything. It could be images, it could be text, it could be other sequences, it could be any kind of object you like, but it lives in this space cursive X here. So we're not going to restrain it too much to begin with. And then what we'd like is some unknown target function that maps objects from this cursive X to another space that we call cursive Y. And cursive Y is the space of outputs, which you can often think of as predictions that we're trying to make for our inputs X. So we have this F, it's there. It represents some natural process that turns the X into a Y, but we don't know it. We don't have access to it. And the whole idea for supervised learning is we'll have examples of X's and matching Y's, but we don't a priori know what this function F is. We want to find something that will act as it, some proxy for it. All right, hopefully I'm not saying anything too out there. What do we get to do? Well, we're going to say first, let's create a space of possible functions that we're going to use to try to model this unknown target function F. We're going to call that thing the hypothesis space. Sometimes it's called the model space. It has different names. It's this cursive H over here. It's just a collection of functions, little h, that go from X to Y. So any of these functions that are in this cursive big H could potentially be the model that we want. And our job is going to be to pick one of those that approximates F as well as we can. All right, everybody agree so far? And this is just mostly notation. We haven't really done anything. Let's go ahead and set up the rest of the problem. What do we get to try to go ahead and get access to F when we are trying to match it with some H? And typically in supervised learning, what we really get is just a bunch of examples. And this is a data set, right? I have a bunch of pairs, X1, and it's matching output Y1, X2 with its matching output Y2, and so forth. I get n of these pairs. This is the only information I really get about what my target function F is. I know that it was used to produce the Y's from these X's. And now I want to go ahead and get an H that is also good at predicting these Y's from the X's. So that's the thing that we're going to try to do. Everybody okay with this? Cool. And we already had an example last time. We said, hey, the X's potentially could be images. In that case, this cursive X is just going to be kind of a space of raw pixels. And then these Y's, in our case, was binary labels, safe or unsafe in this example. And this entire training data set with n points is just n images that someone has gone ahead and labeled as being safe or unsafe. So there is some real function in nature that actually tells you, right, whether a mushroom is safe or unsafe. We don't have access to that real function. We have access to just these examples, and we're going to train a function from some hypothesis class that's going to be able to reproduce this data set, or at least do a good job of making these predictions. And then what we're going to hope to be able to do is to take our function that we trained and take it into the real world, apply it to a new mushroom, and hopefully it'll predict that thing is safe or unsafe correctly. All right, everybody agree with all of this? Cool. Okay, so we've talked about some of the notation. We've talked about some of these objects so far. Really, everything is about these three sets that we've talked about. There's the input space of instances X. There's this output space of all the possible things I can predict or output Y. And then there's this model space H. these are all the things that could represent our target function. Okay, and we've seen some examples of this already. For example, my input space could be made up of feature vectors. These could be continuous vectors that live in some subspace of d-dimensional real space. And in fact, this is really what we want to use all the time because we want to be able to have models that are mathematical functions, and those apply to vectors. Now notice that I don't have to do it this way, right? I could make this x to be anything whatsoever I want. It doesn't have to be vectors. It doesn't have to be anything that has any structure. I can make it raw words, for example. The reason we don't really want to do that is because we'd like to apply mathematical operations as part of our model. So converting this to vectors actually makes a lot of sense. And in fact, getting feature vectors for objects is a big area of machine learning as a whole. Okay, so this is one kind of thing. The output space that we talked about was binary prediction, but it doesn't have to be. It could be other things as well. And finally, we could have things like continuous predictions too. So in that case, I'm not predicting -1 or +1, I'm predicting some value. So let's say I'm predicting temperature, then maybe it's going to be something like 13.23. Okay, so what's the name of the first kind of prediction problem where we're predicting binary things? Yeah, binary classification in particular, and what's the bottom kind of prediction problem?
Regression.
Regression, right. Okay, so that's just some terminology. We're starting to categorize all the different variants of supervised learning. There's a bunch of them, but ultimately all of them will work in largely the same way. We'll just have some slightly different versions of, let's say, the training process, for example. Okay, now continuing, this is exactly what we just said. If we have different choices of this output space y, we're going to give it different names. We talked about classification, for example. Then the elements of this output space are called the classes or labels. It doesn't have to be binary, of course. In fact, the kind of most classical historical version that's over a century old at this point was trying to predict the species of these iris plants. So if you've ever seen this example, which used to be like the very first classification example that people are taught, it's because people were actually working on this well over a century ago. And in fact, what they did is they actually tried to get very specific feature engineering, so specific measurements of different plant features, and then they built classifiers over those to predict this species. Okay, cool. So for continuous, we said regression, and kind of the most standard thing that we ever deal with is linear regression. Of course, it doesn't have to be. We have many other forms of regression as well. Then finally, just know that there's lots of other types as well. So for example, there is a type of supervised learning problem that sits kind of exactly in between that's called structured prediction. So you have lots of different variants here. This is not an exhaustive listing of these things. Okay, anybody have questions or is confused so far? No? Great, cool. Then we're in good shape. Okay, let's talk about the third object. We talked about the input space and the output space. What about this hypothesis class? Okay, so what does this mean? Essentially what we're going to do here is rather than try to permit every possible kind of model when we try to represent our target function, let's go ahead and look specifically for subsets that have some structure. So one example is linear models. Here's how you would describe them. I'm using some slightly unusual notation, but a linear model is parametrized by this vector called theta. I'm going to use this h_theta notation over here. And what that means is these thetas are going to be the weights or parameters of my linear model. So when I take my input x, which is a vector, d-dimensional, what I'm going to do is to multiply each of those inputs, each of those coordinates, with one of the coordinates that's in my weight vector. So theta 1 goes of x1, theta 2 of x2, and so forth. And I'm going to also add a bias called theta 0 over here. So all I'm really doing is forming a dot product, an inner product, with my input vector x, which is a feature vector, and it's a linear operation. Technically, it's an affine operation if you want to be more specific about it, but this is just one simple thing. Okay, so if I just take the raw output from this predictor, is this going to be regression or classification? Yeah, so I mean, this is going to produce some continuous value, right? So this itself could act in regression. If I want to take this and build a classifier out of it, I'll have to do something different. What could I do with it? I could go ahead and take a threshold and say everything above a certain value is predicted to be a 1 or a 0 or whatever. I could convert these guys into probabilities. Lots of different options that we'll see all the time. Okay, cool. So this is one example of a model class. Should I ever use anything that's not a linear model? Why?
Not everything forms a perfect linear relationship with its covariance.
Right. So one issue we might have if we use linear models for absolutely everything is that our target function may have nonlinear behavior. In fact, it often does. So in that case, this linear model is not going to be very good. It's going to have some place where it makes pretty bad predictions. So for that reason, we'll build other model classes. And one example that we'll see in this class constantly is just going to be neural networks. And specifically, let's do feed-forward neural networks, which unfortunately also have many names. If we want to have a very compact version of writing it, it's going to look like this. I'm going to take some input from a previous layer. That's what you're seeing with this little f with superscript k minus 1. This is saying the k minus first layer produced some vector. And now I'm going to go ahead and do an operation on that vector. That operation is going to be something very simple. I'm going to have this weight matrix, wk. Those are the weights at layer k. So I'm going to do wk transpose multiplied by this vector, and that will produce another vector. Now, after I perform that linear operation, I'm going to plug it into this function called sigma. That's an activation function. Sometimes it's called a nonlinearity. And this will produce another vector. This is just the output I get for the kth layer. So all I'm doing is composing two kinds of functions. One is just a very simple linear transformation, and the other is one of these element-wise activation functions. And I do this repeatedly, and now we have a neural network. Incidentally, I can represent any function whatsoever with this guy. We'll talk about why we can't always just use this thing alone in a little bit, but this is quite powerful on its own. Okay, everybody comfortable with this? All right, so what are the parameters for these two models over here? For the linear models, they are the thetas, and for the neural networks, they are
Weights.
yeah, the W's here, which are the weights. We'll use these two terms interchangeably. Weights and parameters mean the same thing for us. There really isn't any distinction. Okay, so if I fix the weights or the parameters, then I have an actual model, right? Any one of these F's or H's over here can be described by a complete set of thetas or W's. Cool. Now, the one thing that you probably don't want to be confused about is, what's going on with inputs versus weights. Weights characterize the model, but I can plug any input into it. X is always the input. W or theta are always the weights. Okay, now, when we train a model, what are we going to vary, the weights or the inputs? Weights, right? So don't get confused about that. That's like the #1 confusion for these things. Okay, awesome. So as we said, the parameters or weights here are the thetas and W. Sometimes we'll have slightly different notation, but these are pretty common. The other thing to sometimes worry about is if we're doing neural networks, there's also biases. Those are also weights themselves. We just give them a slightly different name to distinguish them. Cool. Okay, so now we have kind of all the objects to set up the problem. We know that we have weights that make up our models. These models are supposed to represent a target function. How do we get close to it? Well, we have some data set. The data set has pairs, which are inputs and outputs. So let's go ahead and talk about the actual goal. We want to get one of these H's or F's that represents a target function that we care about. And there's different ways of doing this. But one way of doing it is to say, hey, I'd like to match the data set that I have. And it has a very fancy name that you've probably seen before. It's called empirical risk minimization. Risk is really saying, how many mistakes do I make? Empirical is referring to the fact that I have access to a data set. I would ideally like to have access to the full distribution of inputs and outputs, but normally I don't. I just have this data set. So whatever way we approximate the risk, it's going to have to be empirical, which means I'm working through a data set. And minimization says, I don't want to make mistakes. Get me as close as you possibly can to making the correct predictions, at least on this data set. So this is going to give us this kind of fancy looking equation that we can go through, and it's fairly simple when you kind of unwind it. So let's see what's going on here. Let's suppose that I have some particular model H. That's this little h that you're seeing here. Okay, now what can I do with H? I can take one of the points in my data set, let's say the ith point in my data set, ith instance. That's this thing that's x superscript I. I can go ahead and plug that into my model, my h, and see what prediction it produces. So it'll predict something, and now I know what it should have predicted. That's this y superscript I. So I can plug an x into my model h and compare what I get with what the correct output was meant to be, which is y. Now I have to find a way of making this comparison. I have to find a way to say how close are these two things. I need another function that is going to measure that closeness, and that function is this L called the loss function. So the loss function just tells you, hey, how far off are you? How much of a mistake are you making? Now if your prediction is dead on, if h of x is exactly equal to y, then a normal loss function will give you 0. There's no difference whatsoever between your prediction and what happened. But if your prediction is off, then the loss function will say something over there. Now we can use different loss functions for different kinds of problems. For classification and regression, we almost always use two different kinds of loss functions, but they always measure the same kind of thing. Okay, so what we have here inside the sum so far is for a particular data point, I'm saying my current model h is off by some amount from the true prediction based on this loss function. Now, I could say, hey, give me a model that's really, really good at predicting the correct label of point xi. That would not be super interesting. What I really want is to make sure I'm good over the entire data set. And that's what I'm doing in this summation over here. I'm doing an average. This is the average loss over my entire data set. It's 1 over n sum of the loss over all the data points. Okay, now this holds for one particular h. What I really have is a whole class of models. That's my capital H. And I want to pick out the one that makes this quantity the smallest. Literally, the empirical risk should be minimized. Okay, everybody agree with this so far? Cool. So a fancy equation that really isn't doing too much, is just setting up the problem. We're saying, hey, among my entire hypothesis class, go ahead and pick the empirical risk minimizer. What does that mean? It's saying, okay, well, let's look at the model predictions for each of my candidate models. Let's say, how good are they performing over the entire data set? And this loss function is the thing that's telling us that information. And again, it's averaged over all of my data points. Okay, so far so good? Now, notice that the problem here is that we don't really know how to do this, right? This is just a definition. It doesn't tell us how to perform this actual minimization. Now, you might say, hey, we can try brute force or something like that. Normally, these function classes, the hypothesis classes, are huge. They're infinite. So you can't actually do that. We're going to have to find some optimizers that can actually perform the optimization for us. And that's the subject of a lot of the work that goes into machine learning. What is the most standard optimizer that we'll typically use for training deep neural networks in particular?
SGDs?
Yeah, SGD, and its kind of various related flavors, like Atom, for example. But typically, we'll almost always use gradient-based methods. We're not going to do anything fancier than that. Okay, so if I give you this f hat, that's the output of an empirical risk minimization procedure, one thing that you know, hopefully, if you picked a decent function class, is that it's pretty good at making predictions on the training set, which is this data set that we have over here. But what we really care about ultimately is not how good am I on my training set, it's how good am I on new points that I haven't trained on. And this is the subject of generalization. A model that generalizes does well on new data points, not just on its training set. So this is the thing that we'll generally have to watch out for. It's not sufficient for us to have a very good training error. It's not sufficient to have a low empirical risk. We actually do care about new points. Going back to the mushroom example, I want to take my mushroom safety classifier, try it on a new mushroom, and not die when I go ahead and try it because it says it's safe. All right, everybody happy with everything so far? Cool. Okay, so one way that we'll take a look at how well our model is actually doing is basically by creating a bunch of splits of our data. So if we have access to a bunch of data points, we're not going to train on all of them. We're going to split up those points into sets, and some of those we'll train on, some of those we won't. So typically, we'll kind of have a three-way split. One is going to be the training set that we already talked about. One is going to be a validation set. We don't directly train on it, but we will make some other decisions related to the model, like picking the model class, for example, by using this validation set. And then finally, we'll have a test set. We're not allowed to look at it or do anything with it until we have a final model. We're just going to go ahead and see how good that final model is on this test set that we've kept out. This is also called a holdout set in some of the older terminology. So here's kind of our picture over here. We have all the possible data points in gray. We don't get to actually interact with quite all of them. Only the stuff that's colored is actually stuff that we get access to. We're going to split up this into a train set in red. There's going to be some stuff that we use for tuning, so we're not training on it, but it's still part of this training process. And then this green set over here is a test set. We don't use it for training or selection, just for computing our final metrics. How accurate is our model, for example? Okay, so the number one thing that gets people in trouble, and ML as a whole, is it's very easy to accidentally leak parts of the test set into the training set. And when that happens, you're training on the test set, and naturally, the whole procedure you're doing is going to give you good performance. But of course, on the real test set, which contains of non-leaked points, you may not be doing that well, but you won't realize it. So this is the number one advice for all ML practitioners, engineers, researchers, everybody. Make sure that you didn't accidentally use your test set for training. Otherwise, you'll convince yourself that you have a great model when you probably don't. Okay, questions about this so far? Nope, okay, everybody's happy so far, great. So speaking of what we just talked about, so overfitting is the other thing that we'll have to be very wary of. There's a little bit of notation here. This notation is horrible, so my apologies for it. So let's say we have two kinds of error or risk. One is over my training data. I'm gonna call it error or subscript D over here, which is a capital D for my data set. And to make things really annoying, for my entire distribution, I'm gonna use a italicized D that looks almost exactly the same. We should really use better notation. But these are two different things, right? There is in the world a real distribution of input-output pairs, X's and Y's. And then there's our data set that was sampled, ideally, from that distribution. So I can compute an error over the actual data set, or I can talk about what this error is over the entire distribution. Now, sometimes, if I train a model in a bad way, I can make the top kind of error small, while the actual distribution, that error is quite large. And this is something that you've all seen before. If I overfit, then I have this scenario, and you've probably seen a picture that looks something like this, right? In this case, there's a pretty clear kind of relationship given by that black curve that's separating these blue and red points. That's really what I'm targeting. That's my target function. But I could have a model that's really trying too hard to fit every training point, and it produces this kind of super squiggly set thing. And the reason we always show this picture is that we try to relate overfitting to some notion of model complexity. We say, hey, you should restrict model complexity in such a way that overfitting can't happen. Model complexity here would be something like, how many of these corners do you have? What is the degree of that curve, and things like that. Now, one thing about this class is we'll realize that traditional overfitting doesn't necessarily have to happen with our models. And that's going to be something quite surprising. It's going to lead us to have to rethink some assumptions that people classically made that led to this picture. Questions on overfitting? Cool. All right, we're almost at our first break. One more thing. So we often just talk about accuracy as our primary metric. There are many other metrics that we'll care about. If we're doing multi-class classification, one sort of standard thing to do is to look at this confusion matrix. All this thing is saying is if the true label was meant to be something, but my model made a mistake, what are the typical proportions of those mistakes? If I'm supposed to predict class 1, but I predicted something else, how many of those errors are in class 2, class 3, class 4, and so on? So you depict this thing as a matrix. The darker cells over here are where there were more frequent examples. The diagonal is good, right? It's saying you made the correct prediction. Any of these more shaded areas that are off the diagonal, those are the places that you want to focus on. That's where the model is getting most confused. So make sure you do this kind of thing, do the right analysis, create the right metrics in general for studying your models. Okay, and that's basically the full story at this high level of supervised learning as far as we care right now. The next bit we'll do is jumping into just a very brief review of neural networks. But let's first take 2 minutes. And if anyone has questions, you can go ahead and ask me. And you guys are free to walk around or get a drink of water or whatever. Yes?
Did you decide classes will be
I'm recording right now, so my plan is to do it. Now, like I said, we'll see if it shows up that we might change the policy. But yeah, the plan is yes. It
Large
does.
language models don't need their pre-training data at all.
Right. Yeah, so I mean, this system, yes, but it depends on where we place it, right? So we might say, hey, I'm going to have one particular specialized head built on top of a larger foundation, and over there I'll have very little data to specialize with, and I will need to regularize, for example. It still rolls, but it's not like the traditional thing where that's number one thing to care about, and if you don't regularize the right way, you're here. That's my main message from that. So the problem is exactly the picture that you saw over there. If you have very little data, anything that's weird about this data, right, if you don't regularize, you're for sure going to capture it. But maybe that's not good. Maybe that's not really what's meant to happen in a real distribution.
Essentially, each data point has greater influence on the overall model.
Exactly. We can. Turns out it's not very helpful in general. We can go into all kinds of weird spaces, for example. Right? I can design my models to exist in some space that's not standard real D-dimensional space. The question is, what do I get from it? Am I going to get a better job representing some kind of data? Sometimes the answer is yes. Most of the time, we have to do a lot of extra stuff that makes training harder. So we'll abandon it typically. So this is great. I can make these things work in any space, or I can try to make everything happen in the same space at whatever cost, but everything's more standardized and easier.
One of my friends says it's very difficult to get category first. I
All right, everyone ready so we can keep going? All right, so let's spend again, neural networks are just one class of model. We're not required to use them in particular for any one of our tasks. It's just going to turn out that this is the model class that has a bunch of good features, a bunch of good properties that we actually like. We can scale them up, we can make them very large, we can make them very representative, we can make them work for lots of different kinds of data and tasks. So there are some advantages, which are the reason for why we actually work with neural networks. But again, we didn't have to, and people often had other methods that could be quite powerful as well. Okay, so let's talk about the very simplest kind of neural network. It's so simple that it dates back to the 1940s. It's called the perceptron. So especially in this period, people love these super fancy names. There was also a different term for AI back then. It was called cybernetics, and there was lots of kind of really cool sci-fi-ish notation that nobody uses anymore. Here's the basic story. Let's suppose that we're going to go ahead and classify images as being of cats or of dogs. Well, let's go ahead and take our inputs from these images, and let's form the same kind of linear operation that we saw before. We're going to have for our input a vector from d-dimensional space. Its components are x1 for xd. And for actually performing our operation, all we're going to do is to multiply each of those by w1 for wd, where these guys are just going to be in a weight vector. The weight vector is going to have the same dimensionality as our input vector. The only difference is we might add one more thing, which is going to be our bias. That could be our w0. Okay, so in this case, how do we actually make a prediction? Well, just like we said, we're going to have to do something with this continuous value that comes out. We're going to threshold it in this case. If our dot product, W transpose X, is non-negative, we'll predict 1, which is one of the two classes, and otherwise we'll predict 0. Okay, everybody okay with this? The simplest possible kind of model. Again, the weights are the W's. Those are the ones that we're going to train. Our inputs are going to come in this input vector x. Okay, so as I mentioned, this thing is extremely old. Now, what's bad about this guy? There's a whole mythology associated with the supposed failures of the perceptron. What can this not do? Go for it. Yeah, this thing is linear, so it can't represent any nonlinear functions. XOR is such an example. That is indeed kind of the famous mythological function that, well, supposedly led to the AI winter. Don't take any of these stories too seriously. They're all kind of silly. But this is indeed a problem, and as a result, what we'll do is to kind of go ahead and make it slightly more complex, make it more rich. And to do that, we're going to build multiple layer perceptrons. And these are essentially equivalent to these feed-forward neural networks. Here's a quick example. Notice what I'm doing. If you take just the very first input layer and you consider the way it's connected to one single node over here, that's just like one perceptron. So what I'm really doing here is repeating this perceptron structure, and I'm doing it both in series and in parallel. So at the very first layer, notice that I'm really saying, hey, let's build a bunch of parallel perceptrons. Each one of those nodes is a separate perceptron, and each one of these nodes is going to get connected to all the inputs. I'm not drawing all of them because it's going to get too messy, but that's the basic idea. So what I've done is to create a bunch of parallel perceptrons. Each of them gives me a different output, and now I have some new output vector. Now I take this new output vector and I pretend it's the input to another layer, which again is another series of parallel perceptrons. So again, I have a parallel perceptron, and then I make it the input to another set, which is to connect all of these serially. So I have this whole series of perceptrons, and now I can represent lots and lots more things. I'm not restricted to try to make a final prediction right away. What I'm really trying to do now is to say, hey, I don't know how to do the right answer yet, but extract some information. Tell me something, and those somethings will be stored at the output of each of these layers. And then I take each of those somethings, and once again, I do some operations on them and get a new set of somethings. And I do this repeatedly, and only at the very end of this do I come and go ahead and make my final prediction with one last perceptron, potentially. All right, everybody comfortable with this idea? All we're really saying is I can't directly predict based on a single linear operation applied to the input. Instead, I'll create a bunch of intermediate nodes that carry other information, and I'll do this repeatedly, each time processing the previous set of information until I have what I need so that my final linear operation can extract the correct answer. Now, this is pretty tough to talk about at this very abstract level. It gets a little bit easier if you think of examples. We'll work a little bit through an example with images in a second, but what you really want to be thinking about here is, for an image, I'll start with these raw pixels. Very difficult to make any kind of high-level prediction just by looking at raw pixels. If I want to predict, does this image have a car in it? Just because I tell you this pixel is this color or shade, or this whole array of pixels looks like this, you can't really do that, right? The level of abstraction is just not there currently. When I think of what makes a car, I think of things like, oh, it has 4 tires, right? It has a windshield. It has this particular kind of shape, things like that. These are much higher level kind of things. So what we'll need to do is to gradually extract that kind of information, is there a windshield or not, from raw pixels. But we can't do that in just one operation, right? That's the failure of the perceptron. We can only do that gradually, layer by layer. Okay, everybody okay with this intuition? And you can actually show real examples of it, which is kind of cool. Okay, now let's go ahead and talk about, having taken these models, what do we do to train them? Right, so as a very simplified picture, this is roughly what we'll do. Again, we get our data set. That part hasn't changed. We're still in a supervised learning world. We have n input-output pairs. We're going to initialize the weights of our model, and those weights are basically what all these edges are. All of them are just a component in a weight vector or matrix, depending on how we write them. Initialize those. There's different ways of doing that. And then we'll run our optimization procedure, which is the way that we're trying to solve that empirical risk minimization problem. Okay, so for each of my training points, what do? I'll need to compute a forward pass. This is basically saying, what does my model's prediction look like? I'll go ahead and compute my gradient. So this is taking my loss function, computing the partial derivative of it for each of my weights for my entire data set. That's what this fancy notation is saying. And then once I form this gradient, I make an update to my weights. So I take all of my weights and I subtract the learning rate alpha times this gradient that I've computed. So this is going to be our training process. This is how we're going to solve that ERM problem. We are going to go ahead, compute our network's value. Once we've computed its loss with respect to the correct output, we'll compute a gradient, and then we'll use the gradient to perform SGD or any flavor of gradient descent we want, and we'll update our weights by doing this. Now, notice that this is going to be computationally pretty expensive if our model is big. If you look at each of these gradients, right, we're going to go ahead and form a component with respect to each weight. So if there are billions of weights, which is going to be the case for us, this thing is going to be extremely high dimensional. And on top of that, that capital L includes every data point. So we have something here that for each step scales like the size of the data set multiplied by the size of the model. So that's a potentially huge thing. That is going to be one of the reasons why we like SGD. It's going to let us get away with dealing with a mini batch instead of the entire data set. That said, we still have to deal with the fact that the model is huge. This is where GPU clusters are going to come in. We'll talk more about that later on. Okay, everybody comfortable with this super simplified view of training? Cool. Strictly speaking, this is just vanilla gradient descent, right? So no mini batches formed here, no actual SGD yet. We won't directly use this one for this cost reason. Okay, so all of this was kind of general. Let's go ahead and look at the more specific case that we have for convolutional neural networks. In this case, you're going to form something called a kernel matrix, and you're going to run this guy over all of your inputs. So I'm borrowing the simplest kind of setup that you can imagine. Hopefully everyone is at least a little bit familiar with this, so it's not totally out of the blue. What are we really doing in the case of the kind of data that is good for convolutional neural networks? Well, there's some notion of locality. I don't necessarily care about interactions between, let's say, pixels that are on totally different sides of the image. I really care about stuff that shows up together. So what I'll do is run a small window, which is this kernel or filter, over parts of my input array. And I'm going to say, hey, have I found something there? So we'll perform some correlation or dot product over there. I have my input, which is X, some horizontal array, sorry, some two-dimensional array. I have my kernel matrix, which is this W that sits over it. That's the blue part. I might have a bias that I use, as usual. And then finally, from doing this, I'll get some output. Okay, so hopefully everyone's done this process at least a little bit before. Again, as before, W and B, my kernel matrix and my bias, these are the learnable components here. All right, so when I actually go ahead and do this, what happens? Well, I'm going to create these layers that take one 3D volume and then output a different 3D volume. That's what you're seeing over here. I started off with an image that is 32 by 32, but also has this number of components in the Z direction, which is free. These are the number of channels for colors, red, green, or blue. And then I'm going to run that filter, which is that smaller box over there, over this entire thing. And from this, I'll produce another 3D volume on its own. So we can track all of these things. My input is a box. It's the number of input channels by the height by the width. I'm going to have some hyperparameters which relate to how big this kernel is and how we move it. And I'll have this output box, which is a number of output channels times height times width. So all my convolutional layers are really doing is taking one 3D volume or box, transforming it into another 3D volume or box. And we can easily see what this kind of looks like. Let me show you a quick example. We're going to create this process repeatedly. Here's all my convolutional layers that are operating on what is initially an image and becomes a series of boxes. And then at the very end, what I'll go ahead and do is create just a bunch of vectors. I've lost all the image aspects, and these bunch of vectors are then going to be kind of converted to probabilities using softmax. Okay, so I've gone over this very fast, but hopefully everyone's pretty comfortable with this to begin with. Any questions? Cool. Yeah, so the easy way to look at this is to actually take a real architecture and trace out what the boxes look like. Here is the AlexNet case, which is the first architecture of this kind that really performed very well. As you can see, what it's doing is operating on that input over there, That input is an ImageNet image. These were considered high resolution at the time. They're not that high. It's 227 by 227. So it's a square image. It has 3 input channels because it's color, so there's R, G, and B. And all we're doing here is taking convolutional layers and transforming this box into other boxes. And as we're doing this transformation, there's sort of 2 trends that are going on. Each time, I'm sort of removing some aspect of the image. And you can see that because the actual image itself is getting compressed repeatedly. But I'm gaining more abstract, more high-level features. And you can see that from the fact that these boxes are getting longer and longer. So I'm going from something that is almost entirely kind of a 2-dimensional image to something that is less and less an image and more a set of high-level features. Eventually, I get to the point where there's pretty much nothing in the image at all. I just have a vector. And the vector just has features. And these are the things that really tell you, is there a car here or not, or whatever other class we're predicting. Okay, everybody comfortable with this kind of thing? Cool. Okay, so notice kind of how simple this thing really is. It's really just an older architecture that's slightly deeper and slightly bigger. But already this thing performed really well on ImageNet and was kind of the very first point in this deep learning revolution period. Now, final thing that you should be aware of here, we're not going to make a single output prediction. We're going to really output a set of probabilities, one for each possible class we're predicting. That's this final 1,000 dimensional vector here. The ImageNet competition had 1,000 possible classes for it initially. Yeah?
Just focusing on one layer here, the convolutional layer that goes from 96 channels to 256 channels. How did they determine which channels got the number of, that specific number of kernels to go to the next layer? Because 96 is not going to 56 even number of times.
It actually doesn't have to. That's the other part here. You can make any of these numbers work in any way you want, and the number of output channels is just an architectural choice. Now you might say, why is that the correct number as opposed to more or less? That's part of the magic of designing these architectures. There is not a simple formula. There's a lot of intuition and trial and error. Cool. All right, so we've talked a lot about different kinds of architectures, but they've all sort of been of one type, right? So they mapped one input to one output. The one thing that we should start talking about, because soon we want to deal with text, is what about situations where I don't just have one input and one output? And what I mean so far by one input and one output is we've talked about one image and one predicted class. All right, we had one mushroom is safe or unsafe. And that's kind of the left picture over here. But notice there's a lot of different other things that we could do as well. This one-to-many is especially interesting. Can anybody come up with a case where I would have, the mushroom image as the input, which is 1, but the output is many instead of 1? Go for it.
Classification is like which species?
That still would be really 1, right? Because you would have just one box that could take on all those different values. That is true. That's more fancy than what I'm going for. Go for it.
Something that spits out a variety of recipes.
Yes, okay, so that's a good one. I could take a picture of a cake and just text that contains the recipe could be my output, right? And that's not one thing. That's a series of words. In fact, in general, image captioning is exactly this second box that you're seeing here. I pass in one image, I get a sequence of words describing that image. That's the caption. That's my output. So far, we have not designed a way of doing this. Our architecture so far cannot handle this case. Now, I can also do many to one. You've probably seen this. This is text classification too, right? My input sequence is words, and I could say that's a positive or a negative sentiment. That's very standard. Now, there's other cases like many to many here, and some of these could be exactly the kind of things we are doing with language models. I could ask a question, and I want to get an answer once I've completed my question. That is the one that you're seeing over here. And then the very last one could be something like translation. I start talking, and I expect to get a translation as we go. So we're going to have to design new models that capture this case. But of course, people in the past were aware of this situation, and they created a whole series of different model architectures that did tackle sequence cases. So let's take a look. The kind of most classical example is called a recurrent neural network. I'm going to show one very simple version of it. Notice that I really do have a whole sequence of inputs right now. That is these guys that you see in gold. The X's are the inputs. They're no longer just one object. Now they're a whole series I have x at t minus 1, x at time t, x at time t plus 1, and so forth. And what we're going to do with these guys to build a recurrent model is the following. We're going to start tracking the state of things. That's what that blue box is over here. That little s says, I have some information at the current state that I'm in. And this information will be dependent on exactly two things. One is the previous state, and the other is the current input. So if I'm processing a sentence, up to the point I'm at so far, there's some information, I'm keeping track of it. And when I get a new word, I make an update. And that takes me to my next state. So very kind of classical dynamical system. Everybody okay with that so far? Cool. Okay, now what's the point of this? Well, if we want, for example, to do translation, we'll need some outputs, right? So let's go ahead and take the current state and produce an output based on where we are. That's what you're seeing in those green boxes with little o's. I have an output O at time t minus 1, an output O at time t, and so forth. Now the u's, w's, and v's that you're seeing, those are actual weight matrices that we'll train, but you can ignore them for the time being. Everybody okay with how our model functions so far? It's taking a sequence of inputs, it's tracking a state over time. The state is a function of the previous state at the previous time step and the current input. And each time from my current state, I produce some output. So this output now becomes a sequence itself. There's an O at each time step. It can be whatever sequence we want, including words. Now, how do we train this kind of thing, right? Well, we'll need access to what should be the correct outputs. Well, let's go ahead and get that. Those bright green guys on top, the Y's, those are the outputs I actually wanted. And I can compare them to the outputs I'm producing with my model by, again, plugging these into the loss function. And in fact, I can look at this loss function at each time step. And now I can train in the usual way, except I'm going to train on this whole unrolled thing. So when I'm doing backpropagation, I'm doing it now through time, right? Not just over whatever actual data point I'm currently looking at. All right, everybody okay with this? Just one example of a recurrent neural network. Here's kind of the full list of equations that you need to train this guy. They're actually all fairly simple and easy to implement. What is the main limitation of this kind of classical RNN? Yeah, so I heard someone say it, there's a forgetting problem, right? So the problem here is that all the context that you get has to be stored in that state over there. If you accidentally update the state to forget something important, then whatever you're doing now is going to be pretty bad. And the longer your sequence is, the more likely it is that that's going to happen. So this is going to be a limitation of these kinds of classical RNNs. It's going to turn out that our newer models are going to abandon this approach and perform a lot better as a result. I think I saw a question. Go for it. Oh. Cool. What was an intermediate model before we get to transformers that was better than a vanilla RNN and that anybody with NLP experience probably used a lot? Right. So LSTM's long short-term memory is a variant that is trying to deal with this forgetting problem by essentially being more careful about what gets updated and when. It has this kind of slightly more advanced gating structure in the middle that lets you do that. This thing is actually quite powerful itself, invented in the 90s and kind of reused all the way up until late 2010s. Okay, and the last thing, which is really going to be the subject of our next lecture, is transformers. The story so far that you want to take away is we're going to get rid of that recurrence, right? That's the main thing. We're going to create a new object, which is going to be called self-attention. This new object is the thing that's going to let us get away with no forgetting, but it's going to be expensive as a result. And it's going to be this architecture that you see here. Unfortunately, a bit more complex to understand than just a simple RNN, but we will spend all of next lecture just learning this guy. Okay, I want to spend just a couple of minutes with other things that show up all the time. Hopefully everyone feels comfortable with data augmentation. These are just going to be transformations over basic data points in such a way that we can actually build in a bunch of invariances. So here's kind of the classical example. Suppose that I don't really care about the orientation of my cat image. What I can do is flip it, angle it, etc. It's the same image, it's the same label. I just transform it a little bit. And I show these transformations to my model when I train it. And the reason I'm doing this is I'm telling it you should ignore the exact angle. That's not the key thing to care about here. You should ignore whether it's flipped left or right. That's not important. So that's invariance. You want to build it into your model unless you accidentally want your model to care about very specific facets of your data set. Lots of different examples of this for images, etc. The one thing you might want to kind of recall for this class is if you're doing this at test time, you can also do augmentation. The way to do it is to go ahead and do all your transformations, compute the outputs on those, and compute the average. Any questions?
When you do it at test time, wouldn't it be more useful if you're to try to do different augmentations at test time to see how it would do different augmentations rather than the same one?
It depends on if you're doing this just for prediction or for evaluating your model. If you want to evaluate your model and create some slight differences in your distribution to see how robust it is, you would do that. If you're just saying, hey, I want the best prediction possible, you run the same ones that you did during training. Good question. All right, cool. So let's stop there. We have one more piece of the lecture, which is getting into self-supervised learning. And we'll run out of time. Let's take 2 minutes for a break, and then we'll keep going. Feel free to ask me more questions during.
If like your image has color and you remove the color, could that technically be considered data augmentation?
I mean, people more typically change like the hues and like stuff like that. But yeah, you could do that.
It's like if you have like a medical image or a college image, and you take away the color, it's still the same image, but the pigment of the skin could give more away about what it is. Or without that. I mean, that's just more of a, I think, a challenge.
Yeah, my only concern there basically would be like, if it actually turns out that some aspect of the color is like a critical feature without which your model should not be able to make a prediction, you might like force it to pick up spurious correlations when you use the black and white. So that's the only risk.
Yeah, because like with that, if you have your RGB, like different values of your RGB, then that could also be considered like.
Yeah, that is true. Yeah.
Yeah.
Or augmentation, or in general. Yes. Exactly. So basically, you're injecting some domain knowledge that you have. You know that the real distribution of images your model is going to see are not all, rotated exactly the same, right? And you're saying, hey, I know that's not going to be the case. Let me augment to get rid of that potential aspect. Do you see what I mean? Yeah. So basically what you're saying here, when you're doing these augmentations, is you're saying, hey, I know for sure that this particular thing is not important to my model, right? So for example, if all your images come with the subject of the image at a certain angle in the image, right? If you just train on that, you're telling your model it should care about that. But you know that's not the case. So you're saying, hey, let me go ahead and modify the distribution through augmentation because I know it's supposed to be this. It is only for training, as far as we're concerned here.
At the runtime, if we have say batch data set and we'll augment it in that batch. Then we'll have a mix of batch.
Yes. Yeah, there are like different practical things that you have to deal with then. Overall though. Yeah, okay. That's an interesting question. I don't know what the practical approach people use for that case is. I see your point. Let me think about that. All right, let's go ahead. We'll normally keep our breaks longer, but I want to make sure we finish. Let's talk about what are called representations just for a second. This will lead us into self-supervised learning, which is going to be a departure from all the supervised learning we've talked about so far. Okay, so what's a representation? This is an extremely vague term, but what it's really trying to get at is I want some information about the object that I'll plug into my network, into my model, right? And perhaps whatever raw format that data comes in, usually that's not a good representation for exactly the reasons that we just talked about, right? Raw pixels don't have these abstract things that would help us make decisions about what's in an image. They're too low level for that. So in machine learning, and especially in deep learning, we want to get representations that sort of have all the right information in them that I can use to conveniently and quickly build a model. Okay, and in the very old days, this was basically done manually through a process that was called feature engineering. So there was some domain expert who would take that raw data and they would look at it or play with it in whatever way and extract a whole bunch of features and say, oh, it has this much of this particular thing, this much of that other thing. And this was something that was very painful because you need to hire an expert and have them do this data point by data point. So inevitably, you could only make very small data sets with relatively few features. Now, the reason why deep learning was so successful is that it could get representations that were very rich in a way that was basically automated. So when you looked at that ImageNet case that we were talking about, what that convolutional neural network was doing when it reached the final near the end point where it had all these features is it was finding automatically very useful representations for image classification. And we didn't tell it how to do that. We didn't insist, hey, you should discover this kind of thing. You should build this kind of filter. That automatically happened in the training process. So this is why deep learning was so successful. Okay, so let's take a quick look at actually the kind of filters that it found. These are all from different layers, and you can kind of see, right? Initially, you have very basic kind of things, right? It's the presence of certain shapes and patterns. And all the network is really doing is correlating against all these patterns to form the vector at that layer. But as you go further and further up, these get a bit more general, a bit more high level, et cetera. Eventually, you really have things like, you know, is there something that looks like an animal in the picture? Does it have these properties and so forth? So this is going to be the biggest thing that we do. Can we find good representations for our objects? Now for images, it's kind of intuitive what these are. When we're talking about huge sequences of words, it's going to get a bit more complex in that case. And that's why we'll spend a lot of time trying to figure this out. Okay, so where do we get these representations? I just mentioned one place, which was deep learning. And as I said, it's automatic, so it's very, very, very powerful. But it does have this downside that we started chatting about last time, which is I need lots of label data, right? The reason we could get very good representations for ImageNet is that we do have a data set with 10 million labeled data points. Someone sat down and looked at all of those different diverse images and wrote down, yeah, this is the object in that image. So if we have that much information, that much signal, not surprisingly, we get very good representations. But if we want to do it again for some other domain, then it's going to be very tough, right? We can't recreate that kind of thing in real time. It's going to be very expensive. Okay, now we talked last time about pre-trained models, right? We said, hey, I'm training a model already on some other data set. So for example, I have ResNets on ImageNet, but there is a downside of just using these. And the downside, of course, is, well, whatever new thing I'll do with this representation may not match up with the pre-trained model, right? The pre-trained model was on ImageNet, but if I'm doing biomedical tasks, well, those are completely different things. There's no relationship. Maybe the representations I get from my pre-trained model are not that good. The last thing that we'll often see is the use of encoders from generative models. Well, we will basically do this, but of course one other downside in general is they may not have any relationship to what we actually care about. I can build a generative encoder, but it may turn out that if you use it for a task, it just doesn't do anything for it. So let's go ahead and take some new ideas. Let's try to build representations through self-supervision. This is just what we were talking about before. We have this insight, which is basically that our data set, even without any labels, contains lots and lots and lots of information. We just need to find a way to get it into our model. Okay, so this information ideally is going to be specific to our task. Now what we're going to do is we're going to create essentially a fake task. We sometimes call it a pretext task. And we're going to say, hey, you should become good at this fake task. And here's kind of what we were already talking about last time. Let's say I have images of animals, and that's it. Well, one thing I can do is I can cover up part of the image and ask my model, can you predict what was in that part that I covered up? So this is a task on its own, right? Image completion is a task. But notice that this is not really the task that I ultimately care about. This is a fake task that we made up to try to get our model to become good. And we're going to use the representations that came from that process, and they will have to contain a lot of useful information, right? So you kind of have an idea as a human how to complete that image because you know what's going on at the bottom of it. You know this is a cat. You know that what's going to be on that blanked out part is the head of a cat. And you know lots of stuff about what that head of a cat will look like. We want our model to have the same kind of knowledge. And that's why we're making it do this kind of fake task. Now, of course, later on, we're not going to say, hey, this is the final task that we care about. Instead, we'll do something different. We could do animal classification again. Now, as you see here, there's actually lots of different kinds of these fake tasks. They all involve doing something to our data set and telling our model essentially to undo that. So I could do things like rotate the images and say rotate them back to something normal. I could split it up into little pieces and say, hey, go ahead and solve the puzzle, put them back where they belong. I can do exactly what we were just talking about and remove the color and ask it to recover that color. But again, these are all fake tasks that I can apply to an unlabeled data set. And if I say, hey, model, please go ahead, undo all this damage I did to all these samples, for my model to be able to do that successfully, it has to know a lot about what's going on in the data set. Everybody comfortable with this principle? Cool. Okay, now how do we actually use it, right? Like, let's say I build a model that's good at undoing damage I've done to images. I don't really care about doing that in particular. I want to reuse whatever the model learned for something else. So let's take a look at how we use these representations. As we mentioned, we don't care about the performance on this task itself, but what we're going to do is take the representations that get learned during the process and reuse them for something else different. So let's take a quick look over here. This picture is kind of the easiest way to understand this process. I start on the left. I have lots of unlabeled data, just like those images of cats. In this case, we have some birds. I'm going to run this self-supervised learning process. I'm going to create a fake task. In this case, I went ahead and rotated my bird images. I'm going to say, hey, model, predict how to undo that, which means go ahead and produce a prediction of what the angle was so you can undo it. I'll do that process. I'll run a convolutional neural network over it to do that. And as part of that convolutional network, I'll have a bunch of layers that I've trained. Everybody okay with this first part? Cool. So all I've done so far is say, here's the fake task. Here's a model that's going to perform the fake task. Go ahead and train on my entire data set to become good at the fake task. Now, once I've done that, what I can do is rip off the very end of that model, the one that was making the final prediction of how to de-rotate images. I don't care about that down the line. So remove that part, get rid of it, but take the remaining layers because those are what gives me a good representation. Those layers contain information about these images that are necessary to do well on that fake task. Now I take those layers in particular, and now I can plug this into a supervised learning pipeline. And this means things like predict bird images. And the cool thing about this is I now have good representations. I don't need as much label data. So whereas if I was training on the bird images from scratch, on raw pixels, I would need 1 million data points. Maybe now I only need 100 because I have representations that are very powerful already. They already contain all the information I need to make a prediction. So I no longer need a huge amount of label data. In fact, all I'm going to train is potentially something like a linear model that sits over these representations. And now that's all I need. So I don't even need something very fancy at the end here. All right, everybody okay with this pipeline? And this is going to be basically our foundation model pipeline. We're not going to do it with images typically, but sometimes. Our fake tasks are not going to be things like rotating bird images. They're going to be things like cover up this word and predict what it is. But the principles are basically identical, and you see the value of it. I have tons of unlabeled data. I force a model to give me good representations that understand what's going on in this data. And when it comes time to do actual predictions, I do need labels, but far fewer of them, because I have access to such good representations already. Okay, go for it.
For the base model, the feature extractor model, how will we know that it is getting trained except from seeing that the loss is minimizing?
That's it, right? Now I will hook up the representations that I got from that to something else downstream, and I'll see how they do. Sometimes they'll have no predictive power, in which case we've gotten nothing out of it. But initially, all I do is train that kind of fake task model and see how well it does. Yeah, go for it.
So when you do self-supervised learning, do you do it over one task or you do like over many tasks and then you?
It'll turn out that we often do more than one task. But in principle, we could really just do one task as long as it teaches the model everything that it needs to know. And the nice thing for text is that we're not going to do too many tasks. Next token prediction is going to turn out to be pretty good for everything that we need.
But I remember last lecture you said, when you talk about multitasking model, you said that if you train something on multiple tasks and then you fine-tune it to one task,
Yep.
that returning.
We're going to deviate from that. That is the classical multitask model. Now we're going to say, hey, I can create a very general fake task that's going to be good enough. I'll train my entire initial model, my pre-trained model on that, and I'll specialize to separate tasks afterwards. So that's going to be the difference between classical multitask and the foundation models that we have. Cool, great questions. We have 2 more minutes. Let me very briefly finish up. This is actually the most important slide for this lecture. So as long as everyone's comfortable with this, we're good. Let me briefly mention a bit more notation. So we're going to use this terminology, generative and discriminative, a bunch. Discriminative means we're making a prediction, right? That's it. We don't really care about tracking the distribution of the data. I'm going to plug in some X, I want a prediction Y. If you're doing logistic regression, for example, this is what you're doing. The other kind of version of things is generative. Normally, we're actually tracking a distribution as well. So rather than saying, hey, give me my X, produce the Y, I now actually access P of XY. And sometimes I do this with no actual output prediction at all. I'm just looking at P of X as a whole. Okay, so naive Bayes is doing this, for example. Okay, one more quick thing. If I'm training a generative model, I might just have data points X, and I want to model the distribution P of X they came from. There's kind of 3 pieces that we usually care about. One is, can I compute the density? If I'm given an X, can I compute P of X? Can I do inference? Can I compute P of A given B for some B? And finally, can I sample from my approximation of P of X? A lot of the times we'll end up really only care about sampling, basically. So that's going to be the case with many of our language models as well. These are all things that were trained with generative models. Okay, bear with me for 1 minute. This is our last one. Embeddings and representations are very, very similar. I'll use the terms in slightly different ways, but basically for embeddings, I will just go ahead and take some initial set of objects and produce a very shallow representation that I can plug in. For the classical example is you've seen things like word to vec and so forth. For representations, it'll be deeper, and we'll see what that means in just a second. That means basically that I'm going to have an actual model and use the very last layer before prediction here. So that's the only distinction I'll make between embeddings and representations. We'll talk more about it next time as well. Cool. See you, all of you guys, on Thursday. I'll stick around for a minute for any more questions.